Hey guys, that's Rives here, and today I will be doing a video where I do a parallel transport on the two-sphere, and specifically, there are a couple of videos online where they talk about parallel transport equation, right, and the geodesics as well as the Christoffel symbols, but I realized that there are no videos that actually go through an example of parallel transporting an actual vector on the two-sphere. So we'll do that for this video. We'll go through an example application of the parallel transport equation over here, and we'll be doing it on the two-sphere using this metric. So yeah, I assume that you're already familiar with a metric tensor, which gives you a notion of length, as well as the Levi-Civita connection, which is given by this formula, also known as Christoffel symbols, that can be derived from this metric. And I assume that you have seen at least one derivation of the parallel transport equation, and in this case we'll just be applying this equation to parallel transport a vector on a sphere. So why did I choose this example of S2 is because they always say that there's a common example where they say that to show that the earth is round, then you take a vector and you parallel transport it. You walk along the earth in a path, in a loop like that, and we return back to the original position that you have come from, then the vector will have rotated, and that proves, or that indicates, that there is curvature on the surface of the earth. So in this video I'll be doing exactly that, just that I will be doing it mathematically to show that it does in fact align with your intuition of parallel transport. So what will be the path that we are doing today? So in this video we will be doing the parallel transport along a path which is from so this is the sphere that we're working on. Sorry, it's kind of ugly. This is the sphere that we're working on, and we'll be parallel transporting in a loop like that. So there will be a few points, namely there will be 4 points that we parallel transport it to, so that we would need to transport it 4 times. So we'll be parallel transporting it from pi over 2, 0. So we started from this corner, so pi over 2, 0, pi over 2, 0. Okay, it's a bit blurry. Let me just zoom in. Pi over 2, 0. Then we'll be parallel transporting it to epsilon 0. And the coordinate system in this case is going to be theta and phi. Okay, so this to epsilon pi over 2, and here is pi over 2, pi over 2. So we'll be parallel transporting 4 times from here, 1 to 2 to 3 to 4, and then back to 1. So we'll be doing it 1 to 2 to 3 to 4. So let's go ahead and do this, and back to 1, and we'll see that the whole process will have rotated the vector, which we'll denote by W, from 1, 0. It'll be rotated to W equals to 0, 1. So it'll be rotated by 90 degrees, right? And that will be proof that the two-sphere is in fact, this metric on the two-sphere in fact has some sort of curvature. Okay, so where do we begin? So we begin by calculating. So we're already given the metric, right? So in this case we're already given the metric which is 1 sine squared theta. So we just go ahead and calculate the Christoffel symbols. I won't be calculating them in detail in this video because it's just a straightforward application of this formula, and you can go ahead and use Mathematica or any symbolic software to calculate it, but in the end you should get 3 non-zero Christoffel symbols. So So it will be these three. So the Christoffel symbols we obtain is these two. So these are the Christoffel symbols from the metric, from this metric on the two sphere. Okay, so yeah, okay, so let's go ahead and parallel transport it. So we'll need to derive two types of equations. One is the parallel transporting of the vector along a constant latitude, and that would be yeah, one will be along a constant latitude and one will be along a constant longitude. So what this means is that so in this case the constant latitude is this one with constant theta, with some theta naught, right? So the green ones are the one with constant latitude, whereas the pink ones are the ones with constant longitude. So constant longitude with some fixed variable phi. Okay, so the pink ones are the one with constant longitude. So we'll be needing to derive, we'll be first deriving in the general form for parallel transporting along these two lines, and then later we'll simply apply it to the four steps over there. So yeah, so that let's start ahead. Let's start off with the constant longitude. So constant longitude bracket constant phi, some phi naught, right? And yeah, so what is the path that is taken? Let's just so the path that is taken would be we use the coordinate chart of we in this whole video we'll be working in this coordinate chart of theta and phi. So you parameterize points on the sphere with theta and phi. So the path taken will be this is the parameter, the path parameter tau. So it'll be so let's say this one is a path from theta initial phi naught to theta prime phi naught. Okay, so the path will be then this one plus like this. So this is the path taken. This is just rewriting this as in terms of a function. So in this case, theta is going to be between 0 and 1. So it ranges from 0 to 1. And see that when we start off at tau equals to 0, then x naught 0 equals to theta initial, and phi naught, and at x at 1, there will be equals to this. So this is a path. Okay, so this is the path that we take. So this, where does this fit in the equation? This fits in over here. So this is x mu is the path that we parallel transported along. Okay, so yep. Okay, so then let's go ahead and calculate the derivatives. So so when you calculate the derivatives over here, so that should be rather straightforward. So dx mu tau over d tau equals to, well, most of them are constants, so this is just like this and 0. So this is the velocity vector, which yeah. Okay, so which will denote by v mu. Okay, the velocity of the curve. Okay, so from here, so let's go ahead and parallel transport it. So if we if we look at this equation, right, this parallel transport equation, and we substitute in the Christoffel symbols, then then we substitute in the Christoffel symbols with the only non-zero Christoffel symbols. It results in two equations, one for one for theta and one for phi. So this is the W. This describes how the W theta changes along the path. So D is a differential equation, right? Plus where's the Christoffel symbols? So if you go ahead and do summation over the indices, then you realize that the only non-zero one is the theta phi phi. So you have W phi, and then you have V phi, which is the velocity of the curve, this guy, equals to 0. So yeah, okay, so then for the W phi, you have dW phi over d tau plus there'll be 2 plus this, 2 non-zero ones, the rest are all 0. Okay, so let's go ahead and substitute the Christoffel symbols inside. So we have, this becomes minus, okay, and this one becomes cotangent theta, and this one becomes cotangent theta. Okay, so yes, we have the this is the parallel transport equations for the components, equations, or rather differential equations for components of vectors that are being parallel transported. On S2 with the metric, with the specified metric in the beginning of, with this specified metric, this one. Okay, so yeah, so with this in mind, okay, so let's just take I'll just take a screenshot of this, I suppose. I want to paste it in. So how do I copy this? Can copy it with, okay, never mind, I shall just do this. Yeah, okay, that works, I guess. Okay, so yeah, okay, so with this parallel transport equation, let's go ahead and do it. So okay, so we know that this part over here is v theta and this one is v phi, right? So for the parallel transport along the constant longitude curve, okay, I shall go back to pink color. It will be d this over d tau minus blah blah blah, and then you just have v phi, which is just 0. So this is just this. So you have this one, and then another equation you have is going to be d over d tau plus cotangent theta. Now the v phi term over here is just 0, while the other one is not 0, so the other one is this, and then you have this. Okay, so this is the first one is easy to solve. The differential equation is just a constant, and since we know that it must satisfy the initial conditions, then this will just be whatever initial value it is, this one at t equals to 0. Okay, so this is done. And now what's the second one? Turns out you can turns out this is a differential equation, so this is just a separable differential equation. So minus cotangent and what is theta in terms of phi? Theta in terms of phi is actually this thing. So yeah, so what is theta in terms of phi? It's actually minus cotangent this one initial plus tau prime minus this one initial this one, so yeah, d tau. So now you integrate both sides, so this gives you ln this one equals to minus now you can just apply it. It's just a chain rule, so this is just minus ln sine of initial plus tau minus initial. Yeah, so that's just it, and the end result is that, okay, so if you evaluate this from tau evaluate it from tau to 0 to tau, right? So you just have this one is equals to whatever is the initial one, and then sine initial over sine initial plus tau minus. Yeah, okay, so that is it. Because yeah, you substitute tau and this one into this, and you realize it flips over, and yeah, okay, so now we have the two equations describe now we have the two equations describing the two components of the parallel transported vector as a function of tau. So yeah, so we realize that the first one is simple, it's just a constant, whereas the second one it involves tau in the denominator. So why does it look like that? It's because I mean, if you're parallel transporting along a constant phi, which is the pink one, then you wouldn't really expect the theta component to change. Yeah, I hope that's intuitive, but okay, so now we have this, so yeah, okay, so let's go on to the derivation for the constant longitude, parallel transporting constant theta. Yeah, so what this means is that it's a path from theta naught phi initial to theta naught phi prime. So once again we can construct the path taken. We can write this path mathematically in terms of a function as this. Okay, and then we just have the velocity vector would then be equals to this over d tau, and that will be equals to 0 minus initial. Yeah, okay, so from here let's go ahead and construct the parallel transport equations. So once again, these equations still apply. So we have but we see that there are actually coupled differential equations in this case. So remember that this part is v theta and this part is v phi. So we have sine theta, cosine theta, w phi, and v phi, which is not 0 this time. So we already said that there's mixing between the theta and phi components of the parallel transported vector. So yeah, so and then in the next line we have the second equation, differential equation for phi, for the phi component. So we have cotangent theta. Now we have this. We have theta v phi. So this is this initial equals to 0. Alright, so it appears we have reached the end of the page. Okay, so just keep in mind these two formulas. I shall take a photo of it. Oh, okay, and our previous equation is gone. Okay, but anyway, that shouldn't be too huge a deal. So yeah, let's continue. Okay, so what do we have? We have this coupled differential equation. How do we solve it? So let's just so we write from the first equation, we can write that this one is equals to 1 over sine theta cosine theta phi prime minus phi initial d this. We can write this, and then so we substitute this into the second equation and we obtain d over d tau. Okay, so this one is just a constant term, right? Because this one doesn't depend on tau, because this one is we're traveling along constant theta, constant longitude, and then this one is just constants. So this just gives us the second derivative of the second term. So we get this, right? Second derivative plus, so this is cosine theta over sine theta, this guy, and this. So let's multiply both sides. So we have this plus, now we have cosine theta, and then we have phi prime minus phi initial, and the whole thing bracket squared this. So we see that this is just a simple harmonic motion kind of equation. So the solution will be this equals to a sine cosine phi prime minus phi initial t tau plus b cosine yeah, okay, from now on I'll just call that omega lah, in order to save space. So now your okay, omega is quite a bad variable. Omega, okay, I'll use this omega, okay, where so now I take it as we know that omega is equals to cosine theta naught, right, because it's constant anyway, phi prime minus, yeah, okay, so now we can consider initial conditions. Okay, but before that, so to find a and b, right, so we need to look at the phi component of the trivial transported vector as well. So that can be found from the initial, can be found from from the substituting to the second differential equation. So this is just so we have d over d tau equals to minus cotangent. So this is cosine theta naught over sine theta naught, phi prime minus phi initial. So the numerator is just omega. This. Okay, so we integrate both sides. So you just get this one is equals to so integral of both sides, you get a. Okay, so it is 1 over sine theta naught. So you get you get a cosine omega tau plus b sine omega tau. Okay, so what's the initial conditions? So what is a and b? So we sub t equals to 0. So omega, this one, equals to initial, and from this one you get that is equals to b b. So that's your initial, that's what your b is. Yes, so that's what your b is. And then for your a, so for your a is this equals to, and you substitute into here, so you get a over sine theta naught. Yeah, okay, so fair enough. So in the end we get that so I think we're done with this. So in the end, what's the two equations? We have omega w theta is equals to w w phi initial sine, this one, sine omega tau, right? So this is the path dependence, plus what's your b? Your b is this guy from here, cosine omega tau. And then how about phi? For your phi, we have for your phi we have this guy, right? So what is this? So it's this initial cosine omega tau plus this over sine theta naught sine omega tau. Okay, so oh yeah, apologies, I believe I missed the minus sign over here. Yeah, because when you integrate this, there was a minus sign over here. So yeah, sorry about that. That doesn't affect the initial conditions. So yes, so these are the two equations, which let me just do a quick check with my cheat sheet beside me. That is correct. Yes, it looks correct. Okay, that's great. So these are the two equations. So in the end, we have had okay, so we have had yeah, so now we have derived, we have successfully derived the equations for the components of the parallel transported vectors along the constant longitude and the constant latitude paths. So now all that remains is to apply them to the path that we have chosen. So I will go ahead and screenshot this one. Okay. Okay, and I will screenshot the other one as well. So this one, so okay, I'll just write this. I'll just write this one down here. Okay, so these two. So we have these two equations. So yeah, so we are ready to finally do the parallel transporting. Okay, so yeah, okay, so remember that we have chosen the path from to be from the first one. It will be from this guy pi over 2 0 to epsilon 0. So the first one will be from, we start off with the vector. Okay, so we start off with the vector this vector, this 1 0 vector, and then the first one will be from pi over 2 0 to epsilon 0. So what would this be? This would be along the constant phi, which is the constant phi, which follows the pink one. So it follows the pink one. So what is the pink equation? The pink equation is so it tells us that w theta is now equals to 1, right? Because it's just equals to the initial one, and then w phi is equals to this thing, but the initial is just 0, so it's just 0. So after that we end up with 1 0 again. Okay, so now the next step will be to go from epsilon naught to epsilon pi over 2, and this will be the green one. So let's see the green equation, and what would that be? That would be from, so now it will be the initial, so we substitute the initial for, so it's just 0 times a bunch of things plus times plus 1, right? So now this becomes the initial. So the previous final answer is now the new initial value. So this will be cosine. Okay, what is the big omega? The big omega was equals to the big omega was equals to cosine theta naught phi prime minus phi initial. Yeah, so this case is cosine theta naught. What is the constant? The constant theta naught is this one. And then what is the phi prime minus phi initial is just pi over 2. So well, yeah, so actually bracketing this whole thing. So it's a bit funny, but in the end, this is just equals to cosine pi over 2 epsilon. Okay, and what is the phi? The phi will be equals to the phi component equals to the initial, this one, which is just 0, right, plus 0 plus 1 times sorry, it's 1 over, sorry, it's not plus, it's minus 1 over sine theta naught sine omega t. So there will be omega t is once again this one, pi over 2. Sorry, it's not, sorry, this one is cosine this one, so this one should be cosine epsilon pi over 2. So that's even funnier. Yeah, okay, so this is going to be pi over 2 cosine epsilon. So that will be so that will be hey, but something smells a bit fishy. Sine hmm hmm there's a minus sign here. Okay, so there'll be minus sine pi over 2 cosine epsilon over sine theta naught, and theta naught is epsilon, so yeah. Okay, so yeah, sure. Okay, so then the I believe this differs from my cheat sheet, but I think I don't think I made a mistake. Okay, sure. So then the next one, so it's going to be epsilon pi over 2 parallel transported to, okay, so give me a moment, I need to, okay, so sorry, I had to okay, so I have to respond to something. Okay, so this one, the next step will be from this one to pi over 2. So what would that be? So there will be a long constant longitude again, so we are looking for the other equation. So then this one is equals to, it doesn't change at all, so this is pi over 2 cosine epsilon, and this one phi equals to is equals to the thing initial, so that will be minus sine, so this thing substituted in, and then you have your sine the initial, sorry, this is epsilon, so the initial is this guy, right, over sine the final, which is this guy, so this just this, which equals to minus sine pi over 2 cosine this one over sine pi over 2, which is just 1, but yeah, which is just minus sine pi over 2 cosine this one. Okay, so finally the fourth parallel transport will be from pi over 2 to pi over 2 to all the way back to pi over 2 0. Alright, so as we are running out of space, this is just nice. It's along a constant theta again, so we bring up the green one. Okay, so this is just, so with respect to the previous initial conditions, this is just this equals to phi initial, so sine pi over 2 cosine this one times the sine of pi over 2 as the theta, this is a theta naught now, so this is theta naught, right, and then you have your sine omega t, omega tau, which is going to be omega is equals to, omega in this case is equals to cosine pi over 2, so phi prime minus phi initial, which is just cosine pi over 2 is just 0, so it's just 0, so sine of this one is just 0, which brings the whole thing to 0. so then plus the, so it's just 0 plus the theta initial, which is cosine pi over 2 cosine epsilon, and then cosine 0. So that's just that. Alright. Okay, so yeah, okay, fair enough. Alright, so after that, your phi is equals to this one is equals to that thing phi, so substitute these guys in. So what is the phi initial? It's just minus sine pi over 2 cosine this one, and cosine of 0 is just 1, and then you minus the theta, right? But then that sine of omega tau is just 0, so that's just 0. So this is your final result, and yeah, so yes, and then if you take the limit that this one goes to 0, you realize that you are just parallel transporting something like in all the way to the north pole, right? So you take the limit that this one goes to 0, then you just get cosine this one goes to 1, so you just get cosine pi over 2 for the first one. So then this one converges to 0, and phi converges to a minus 1. Okay, so we see that this one is the vector minus 0, 0, minus 1, and hence our vector has rotated from from 1 0 to 0 minus 1, and by parallel transporting in a loop like that, we have observed that the vector has rotated. So even though the vector is gone in a loop back to the same place, it is rotated due to the curvature of the sphere. So yeah, that's how you parallel transport a vector along a sphere from the very beginning, from starting from the metric, calculating the Christoffel symbols, and then using the Christoffel symbols to formulate the parallel transport equation, and then the parallel transport equation gives you the differential equations for the components of the vectors, and in the end you just follow it along the path, substitute in all the paths and solve the differential equations to obtain how the components have changed when you go a loop. So I hope that you've enjoyed this video. If you did, please leave a like and subscribe. Have a nice day. Bye.